For this week's update, I'm going to go over Charlie's main controller block diagram and go over the block diagram for the display that was created. So this block diagram has been implemented in a control board already, and it hasn't been populated yet. So that's kind of the next step, is to go through that and get it stuffed and test it and start the installation in the main head of the where the headlight and display and all that located. So with the controller block diagram, this is kind of describing all that is on the circuit board. Now the approach I took was to take an eval kit from Neotone, and so this is their NUC 140 development board, and it has nothing really on it except bare minimum. You know, it has its crystal, has I think a USB connector on it for plugging in, and has most of the I/O broken out into headers. So that is like ideal for what I'm planning to do, and it's just a matter of putting all the extra circuitry down that's needed to condition the signals from, you know, the brake levers, from the throttle, to control the headlights and the horn, and to be able to control the display, as well as provide control of the main contactor that's going to be located down near the battery. So just looking at the block diagram, you can see it's got quite a bit of stuff in there, and this is a fairly small board, and being, you know, two layers and milled out, you have limitations as to how much you can actually put on the board. If this had been a regular PCB that's been made, I may have attempted to put the NUC down rather than putting down a second board, but this is a much easier way of doing it for you know, attaching it to a milled PCB board. So if you look at the block diagram, we've got two circuits blocks for the analog brakes, and, you know, a left and a right, and this is to allow some options for how a linear analog brake sensor might look. And, you know, you can use a Hall sensor, and you can use, you know, a potentiometer. There's different things you can use to translate the linear motion into you know, ADC value. I haven't yet figured that one out. That's kind of a little bit further along after I've gotten this board up and running. In the short term, if I don't have a solution for that, I have digital inputs for just, you know, Hall switches in the brake levers for cutting the motor. They're really simple, just doesn't give you the opportunity to do any regen braking. I also have a throttle conditioning block as well. I mean, the Hall sensor that's going to be in the throttle is going to translate the rotational motion into a voltage that, you know, the ADC is going to read. There's not a lot you need to do that, but still there's some filtering that's on there. There's a speed sensor blocks, and that's going to take the Hall sensor, speed sensor that's located on the front wheel, and translate that into a clean pulse train for the controller. There's also a menu navigation button. So this is a PlayStation joystick slash selector. So there's a X and Y direction that, you know, you translate your motion of your joystick into an X and Y value, and there's also a selector switch. So that's going to allow me to run up and down a menu that's going to be displayed on the OLED. And again, this is much further along. There's a quad high side driver, and so this is a high side switch that's protected, and there's four of them. And rather than having a mechanical switch to switch on power to a headlight or horn or whatever, you have essentially a MOSFET that connects it to the 12 volt supply. And this is a little bit cleaner way of doing it, because the controller can decide, you know, if it's on or off, and You don't need any heavy gauge wires or anything to go to your headlight buttons and horn. So it's just an easier way. It's protected. You know, you don't have to put fusing in there. It's just a nice way of being able to control that sort of thing. The other thing that the quad high side driver is doing, so two of the channels is dedicated to the horn and the headlights. One channel is dedicated to providing the source power for a contactor that's located down by the battery. Now this is going to wrap into sort of a watchdog for keeping track of, you know, whether or not the main controller is alive or whether or not the motor controller is alive. You know, DC control is notorious for runaways, so when a bridge fails, you know, it usually fails with the motor being connected to the battery, and then, you know, everything just goes nuts because you can't stop the motor unless you got a contactor in series between the battery and the motor. And that is what I'm planning to do. But I'm also having two methods to, you know, terminate the contactor so that it can disconnect the motor. So down at the motor controller, there's going to be a low side MOSFET essentially that's going to allow me to open that up, as well as the high side switch. And so I have two ways to remove power from the contactor. The battery itself comes up on a line through one of the connectors, the Microfit Junior connector, and then gets wired out to the throttle, which has a key switch on it. So that is the main way of turning power on and off to the scooter. And you know, it returns back the switched battery power, which then powers up the or is down converted to 12 volts and 5 volts. So 12 volts is for the headlights, horn, and contactor, and the 5 volts is for running all the logic. The primary way of talking to the motor controller is through the CAN network, and this is chosen because it reduces a lot of the harnessing requirements between the motor controller and the main controller. 'Cause, you know, CAN is two wires and a ground reference, so that's pretty low. So if you think about what's going down between them, between the main controller and the motor controller, you've got, you know, two wires for the CAN, one wire for the ground reference, so that's three wires. You've got the source wire for the contactor, and yeah, that's pretty much it for between the motor controller and the main controller. So obviously there's two more additional wires that come up from the battery, but you know, there's not heck a lot else going between the two. The display is controlled, or you talk to display through I2C, and that is again a way to reduce how much wiring that you need to you know, move information back and forth between things. So if we look at the display, you know, this was done a few episodes back, where I created a display that would fit within the old footprint that the old display had, as you know, and the light switch. The only thing that had to be changed was there was a slot that had to be milled for the state of charge, or the, you know, the battery indicator. So again, it's a very simple circuit. You have an I2C buffer that, you know, isolates the capacitor loading of the devices from the master, which is the NEUC controller, and there's two 16-bit port expanders which give you enough lines to drive the three 7-segment displays and the 10-segment bar LED display. And I initially had too low of resistors in there, so the power consumption was huge on this board. I, you know, have since bumped up those resistors to reduce the current that's being sunk into the port expanders. There's a E² on there, which I'm not sure what I'm planning to use it for. There's a good chance that I might just use it for, you know, data logging hours on the battery or something like that. I don't know. It's just extra memory that's in the system that's easy to access. And then the other one is the OLED display. So this is a 128 by 32 OLED display it's pretty small. It's only like I think it's like 0.9 inch wide, and that's the circuit board portion of it. I think the actual display is a little bit smaller. And at the moment, I haven't got any of the firmware in place to really do much with it. I have to rewrite my I2C drivers so that they are non-blocking in nature. I may change my mind and put an RTOS on this. So an RTOS, for those who don't know, it's pretty much like running a whole bunch of you know, individual controllers, and you have a clock that's running in the background. It just says, okay, your time's up, let's move to the next thread or next controller. And so what you can do is you can have I2Cs that are just sitting there, like handlers that are just sitting there, you know, waiting for something to complete, like waiting for the transaction to complete before starting up something new. And that doesn't stop anything else from running. It makes your driver a little bit simpler, but then you also have to have an RTOS running, and there's lots of open source ones available to run, but I haven't decided yet how I'm going to approach that. So again, pretty simple stuff for at least the display and the controller. The motor controller is going to have more complexity in it, because with that you have to deal with very fast transient currents and voltages. So the layout is more critical, and I'm not sure that I want to attempt to do it on a milled PCB yet. I may just do it for an attempt at seeing whether I can do it, but the copper weight of board has to be at least 2 ounce, and the stuff that I have right now is all like ½ ounce. You sneeze on it and it peels off. So I'm gonna have to decide what to do, but that's probably going to be coming up in 3 weeks or 4 weeks, depending on how long it takes me to finish putting together the plastic for holding the main controller board at the handlebars, and how long it takes me to come up with the brake sensors, and it just takes time. Anyways, thanks for watching.